AI is literally breaking traditional data centers. Today's explainer rips apart a massive shift in how we build AI clusters, focusing on a game-changing breakthrough, Open CPX. Let's get right into it. So here's the deal. To scale AI up, we need 10 times more capacity just for XPU connectivity. 10 times. If your current data center is a garden hose, AI is basically demanding a fire hydrant. The old ways of moving data around, they're way too slow, and honestly, they burn way too much power. We desperately need a new physical architecture to handle this bandwidth explosion, and that is exactly where OpenCPX comes in.
Section 1. The bottleneck. Evolution to co-packaged optics. For years, optical connections just sat comfortably on the front panel of the switch. But at AI scales, pushing electrical signals all the way from the central processing chip, the ASIC, to the front panel is a huge problem. You lose too much signal and burn way too much power. So the industry's answer is to move the optics as close to the ASIC as physically possible. But there's a massive divide in how we actually pull this off. Proprietary co-packaged optics versus the open socket approach of OpenCPX. Proprietary solutions tightly bind the optics directly to the ASIC package. Sounds super efficient in theory, right? Well, in practice, it's an absolute nightmare for large-scale economical deployment. That tight integration completely locks you in. OpenCPX, on the other hand, is designed to decouple these technologies. It gives engineers their flexibility back.
Let's break down exactly why these proprietary setups are basically a trap. First off, single vendor login. I mean, if your one and only supplier has a hiccup, your multi-million-dollar AI cluster deployment just grinds to a halt. But the real killer? Compounding yield failures. When you permanently attach optics to an ASIC, if just one tiny optical component fails during manufacturing or out in the field, you have to throw away the entire incredibly expensive ASIC package. It's crazy. It also completely eliminates your choice to use copper and leads to terrible serviceability since you can't just swap out a bad part when things go wrong. Section 2. The breakthrough. The OpenCPX Multi-Source Agreement, or MSA. So, how do we actually get the benefits of co-packaged optics without those catastrophic yield and lock-in risks? Well, this is where the OpenCPX standard really shines. Over 80 companies have already joined this MSA. We are talking about a massive, versatile ecosystem here. Component suppliers, connector manufacturers, IC designers, system integrators, the whole shebang. This ensures massive supply resiliency. You're no longer relying on a single company for your optical engines. If one supplier gets backed up, you've got dozens of others building to the exact same open socket standard. The true superpower of this standard really comes down to one word: decoupling. By using a pluggable open socket, OpenCPX completely separates the testing and assembly of the optics from the final ASIC assembly. It's a game changer. You can individually test these connectorized optical engines before you ever install them next to the core chip. This completely solves that compounding yield crisis. If an optical engine fails a test, you just replace a relatively cheap plug, not a multi-$1,000 ASIC package. And because the socket is open, the industry gets to leverage highly mature, field-proven silicon photonics. You don't have to roll the dice on bleeding-edge, unproven proprietary tech. You can use optical components that already have incredibly reliable failure in time, or FIT, metrics. We're talking well below 0.1 FIT. So to put that into perspective, when you deploy these massive scale-up AI clusters, you can do it with absolute confidence that the underlying physical layer is just bulletproof. Section 3. The blueprint, form factors, and deployments. Okay, so how do we actually integrate these open sockets into real physical hardware? This standard gives us two primary connector types to handle this extreme density. Type 1 has a separate RF connector from the power and control connector. This gives you incredibly high flexibility for complex multi-plane connectivity, and it supports both internal and external lasers. Type 2, on the flip side, is all about purpose-built simplicity. It integrates the RF and power into one streamlined connector system. Basically, it gives hardware designers exactly the tools they need based on their specific space and power constraints. Now, this brings us to a really innovative deployment concept called IOA, which stands for Integrated Optical Attachment. Think of it like this. Imagine a very low-loss, high-performance circuit board directly attached to the ASIC substrate, acting as an extension. This IOA creates a sort of hybrid zone. It perfectly bridges the gap between traditional architectures and full co-packaged optics. You can attach either copper or optics directly onto this high-performance extension, which vastly reduces signal degradation. The true beauty of OpenCPX is its adaptability across different stages of hardware evolution, First, for standard scale-up, you can just place the engine right on the main printed circuit board, right next to the ASIC. Second, for true CPO, if the ASIC substrate can actually be opened up, the socket drops directly onto the substrate itself. And third, like we just talked about, the IOA method, attached to a substrate extension. This just proves that the standard can adapt to almost any thermal, spatial, or architectural environment an engineer might be dealing with.
And all of this incredible flexibility perfectly serves a really famous hardware engineering rule of thumb. Use copper when you can and use optics when you must, right? Copper is cheaper, it takes less power, but it simply can't push high bandwidth over long distances. Because Open CPX defines a universal socket, hardware designers can literally mix and match. They can deploy a cheap copper plug for short runs and then just swap in a high-performance optical engine for the long runs, all within the exact same socket design on the board.
Section 4. The Future, Real-World Impact and Roadmap.
So you might be wondering, is this actually happening out in the wild? Absolutely. Let's look at a concrete example, the Terra Optics Diablo 1. This is a 6.4 terabit optical engine that uses that flexible Type 1 connector we mentioned. And what's absolutely vital here is that it uses silicon photonics that already have over 25 million field-deployed units in standard transceivers. By taking that highly mature low-failure technology and putting it into the OpenCPX form factor, they instantly brought carrier-grade reliability into the bleeding-edge co-packaged optics environment. That is a massive de-risking for data center operators.
To see how this works at the system level, take a look at the Arista AS600T switch. It features an ASIC surrounded by 16 Open CPX optical engines, utilizing that IOA setup we broke down earlier. The brilliant part here is the physical layout. They're using direct pigtail fibers running straight to the front panel. This entirely wipes out failure-prone external interfaces and the huge risk of optical contamination during installation. Plus, there are separate cooling cold plates for the optical engines. This makes thermal management and physical serviceability an absolute breeze compared to those proprietary, glued-together setups. The momentum behind this is seriously accelerating. Looking at the roadmap, the Open CPX MSA is delivering Generation 1 right now, bringing 6.4 terabit engines running over 8 parallel lanes, also known as DR8, to the market. But as we know, AI isn't going to wait around, so the next generation immediately targets a massive expansion to 12.8 terabits per socket. And looking just slightly further out, they're gearing up for full support of Advanced Optical Connectivity Initiative standards, or OCI PMDs. This ensures the industry stays totally aligned on capabilities, and the ecosystem is moving fast enough so the physical layer never bottlenecks AI compute. By solving the yield crisis, destroying vendor lock-in, and leveraging mature silicon photonics, OpenCPX isn't just a new socket, it is literally a lifeline for AI infrastructure. The transition from copper to tightly integrated optics, it's inevitable, but how we manage that transition changes everything. So I'll leave you with this question to ponder. As bandwidth demands continue to explode by factors of 10, how will open hardware ecosystems like this ultimately redefine the physical limits of what an AI data center can achieve?